Hello all and welcome to this fourth video in our series where we look at matrices. In this video we will be looking at finding what is the identity matrix and then finding the determinant of a matrix and then the inverse of a matrix. The reason we need these, well, identity is more of a proof of why we need the second and third items. And we need determinants and inverse because we're going to need these to be able to do division. We've already done addition, subtraction, multiplication. Now that we're missing division, we'll eventually be using this principle here. So instead of dividing, so we could do, for example, let's go A divided by B. Well, that is the same as A times by 1 on B, which, as we can see here, 1 on something, we can also write it as instead. Sort of remembering index laws, we can bring this up to the top and write that as with a negative pair instead. So we can now write this as A, B to the -1, or we call that the inverse of B. So we need to be able to find we're going to use this idea of, instead of dividing by, and if we put this in matrix form, so capital letters, instead of dividing by the matrix B, instead what we're going to be able to do is multiply by the inverse of B. That will give us the same result, just using this as a simple, I guess, proof here. But that's why we need to be able to find the determinant, because we need the determinant to be able to find the inverse. But yeah, that's why we're doing all of this section. So this whole video is purely looking at finding the determinant and the inverse. It's not even doing any division. It's just finding those. So first off, let's look at the identity matrix. So the identity matrix is just any matrix where everything apart from what I'll call the main diagonal, everything else is 0. And the identity matrix is given the capital letter I for its name. Doesn't matter how big it is, it could be a 2x2, a 3x3, a 4x4. It just needs to be a square matrix where the main diagonal is all 1s and everything else is 0. Now what's special about the identity matrix? Well, this is sort of the equivalent of 1 in the matrix world, because if we do the identity matrix times by any matrix, we could call this A, we could call it B, doesn't matter. We're just going to get the original thing. It's just like multiplying by 1. The identity matrix is the matrix equivalent 1 times by A gives us A, or if we did A times by I, we still get A. So it doesn't matter what order we do it in, multiplying by the identity matrix gives us our original matrix. So the identity is the equivalent of 1 in matrix form. That's all it is. It's a simple definition. That's all we need to know for now. Right, on to finding the determinant. The determinant of a matrix is just a single number. So to be clear, it's not a new matrix rewritten, it's just a single number. There's many uses for the determinant, but we're just going to be able to use it at the moment just to find the inverse of a 2x2. So all this inverse and then doing division of matrices, we're not going to do it to anything bigger than a 2x2 matrix. Actually, we're only going to do it to a 2x2 matrix. We're not going to do it to a 2x1 or a 1x2. It's just 2x2s that we're doing. Now, how do we find it? Well, if you're looking at this animation as it's rolling now, we'll take what I call, and I'll highlight it in red, we call this the main, or I call it the main diagonal. For lack of a better term, the main diagonal, and then we also have the secondary diagonal in blue. So red is main, what I'll call from now on, and then blue is the other, or yeah, just the other diagonal. And all you do is, for any 2x2 matrix, for the determinant, you're going to take the main diagonal, the two numbers in the main diagonal, multiply them together, which is what's happening here. And then you're going to take the other diagonal, multiply those two together, and you're going to do this subtraction between the two. So it's a bit weird here watching, and I'll write it out in full because it keeps disappearing. So we get AD minus BC. So you multiply the main diagonal, that's our AD, and then you subtract the other diagonal multiplied together. And it's going to give you a number because these will just be numbers. So really quickly, as a quick example, we've got 3, 1, 2, 4. You'll do the 3 times 4, which is the main diagonal. So 3 times 4, take away the other diagonal, which is 2 times 1. So you get 12, take away 2, gives you 10. So this is called the determinant. It's just a number. It's not another matrix or something. It's just a number. Because we're using diagonals, we can only calculate the determinant of a square matrix. So again, this locks us into a 2 by 2. Technically, there's ways to calculate it for 3 by 3, 4 by 4, but we're not going to do that. It gets really, really tedious. We're just going to stick to 2 by 2s. So main diagonal, take away the other diagonal. Here it is again written out. Or no, sorry, that's the inverse. But we'll just stick with the determinant now. It just gives us a number, and then we can write it as whatever the matrix is. We may have had this initial matrix called A. Well, this number we write as determinant of A, or sometimes you'll see it written as like that. Determinant of A is some number. Yeah. We need this to be able to find the inverse of a matrix. This will make up part of the inverse. Okay. So let's say if we start with some matrix, A, D, or A, B, C, D, and I've highlighted again using the colors, the inverse is equal to this bit here. So we can do this for 2 by 2 matrices. It's 1 on AD minus BC, and we've seen this. We just did this on the previous page. That's called the determinant. So that bit underneath is just the determinant of A, the original matrix. And then looking here, we have to do some stuff to the actual matrix itself as well. It's not just this number out the front. We have to do some stuff in here. If you look carefully at the main diagonal has been switched. It's flipped. The A and the D switch positions. See, D is now top left and A is bottom right. So the main diagonal switches positions, and then the other diagonal, they're just made negative. You can see here they're just made negative. So they don't switch positions. They're just made negative. And that's the inverse. That's all it is. Now we can prove that these are the inverses, because if we think of A divided by A, well, that's going to be equal to 1. If we just think back to regular numbers, say 4 divided by 4. Yeah? We could do 4 divided by 4, that's equal to 1. Yeah? Now, I said before we could write this 4 divided by 4 as 4 times by 1 on 4, which is equal to 4 times by the inverse of 4, and that is also still 1. Now, we could take this idea here where we could A times by the inverse of it gives us 1. We do A in matrix form times by its inverse, that should always give us the identity, and that's the way we can check our working out. So this is where this formula to give you the inverse comes from rearranging this thing here and doing some fancy stuff, but just we can take it as stated as fact, that this is what the inverse of any 2 by 2 matrix is. Now, there's a couple things we need to note looking at how this is formed. Okay. First off, it has a determinant in it, so we can only do it for 2 by 2 matrices. Sorry, not 2 by 2. We can only do it for square matrices, because the determinant only exists for square matrices. Okay. Also, important is sometimes you might get a special situation where this determinant is actually equal to 0. And we are not allowed to do 1 divided by 0. So if the determinant is either equal to 0, as it says here, then that actual original matrix, whatever we started with, doesn't have an inverse. An inverse doesn't exist. You can't find it. So those do happen. I think that's everything on this slide. Let's have a look. Yeah, we flip the main diagonal and we make the other diagonal negative. there's two key points. We can only find the inverse of a square matrix, and if the determinant of a matrix is 0, then no inverse exists. So there's an example. Consider the matrix B, that's equal to 1, 2, 3, 4. If you're ever asked to find the matrix, or you're ever asked to do the division, the steps to break it down is 1 is find the determinant. Okay, find the determinant of B or A or whatever it is, and then 2, write out the inverse. And then if it is also a problem that involves division, then 3, you'll then do the multiplication by the inverse, but that's being left to the next video, so we just leave that. But first thing is, don't try and do this whole big formula this way. It's much easier to go, let's find the determinant individually, flip the main diagonal, make the other diagonal negative. It's 3 steps to remember. So in this case, B is equal to 1, 2, 3, 4. So the determinant of B is equal to 1 times by 4, which is the main diagonal, take away 2 by 3, so it's equal to 4, take away 6 is equal to -2, which is what it says there. From that, we can say then the inverse of B is equal to 1 on the determinant. So we just put in our -2, which we found, put in our brackets, and we're going to look at the main diagonal and flip that. So the 1 and 4 change places, and then the 2 and 3 stay where they are, but they're just made negative. And that's it. There's our inverse. Now you could multiply this fraction inside, so this could turn into 4 divided by -2, -2, -2 divided by -2 is 1, -3 divided by -2 is just 3 on 2, and that turns into -half. So you could write it in either form. This top line's right, and the bottom line's also right. And if you multiplied this inverse that we got, as I was saying on the previous slide, if we multiply it by this original matrix, you will get I. And if you don't get I, either you've done your multiplication wrong, or you made your inverse wrong, because it needs to give you I. That's how the inverse is defined. Right, so let's do some examples. We start with this. Let's call this A, that's B, that's C, that's D. Okay. So first off, is it a square matrix? And we're just going to deal with 2 by 2. So yes, so we can find the inverse of this. So the determinant of A is equal to 4 by 3, take away 6 by 1. That gives me 12, take away 6, which is equal to 6. So the inverse of A is equal to 1 on the determinant. Then we are going to flip the main diagonal, so 3 and the 4 flip places, and then the 6 and the 1 just become negative, so -6 and -1. And again, you could multiply that 1/6 through as a scalar multiplication to simplify, which would turn into half, -1, -1 on 6, 4 on 6, which you could simplify into 2 on 3. There you go. Okay, for example B is not square, therefore no inverse exists. On the C, it's a square matrix, so we can start, so we need to find the determinant. So the determinant of C is equal to 2 by 2, take away 0 by 0, which is equal to 4, take away 0, which is 4, which is not 0, so we can go on from there. So the inverse of C is equal to 1 on 4. We switch the main diagonal, which is just 2 and 2, stays the same, and then we make 0 and 0 negative. Well, -0 is still just 0, so it stays the same. We can bring that through, so this is going to turn into half, 0, 0, half. And there's our inverse. On the D, it's square, so we can attempt to find the inverse of it. So let's find the determinant first. So the determinant of D is equal to 3 times 2, take away 1 by 6. We get 6 take away 6, which is equal to 0. So since the determinant of D is equal to 0, this is also our other case, no inverse exists. Because if you try and do 1 divided by 0, you break mathematics. You can't divide by 0. So there we go. You can find them on the CAS. Pretty straightforward. I still have some of the matrices that we put in the last video. So we had this A, which is 1, 45, 2, and 4 stored as A. We can go, you should be able to just type in A to the power of -1, and it's instantly found the inverse of it for us. And if we then do A times by the inverse, we get the identity matrix. That's it. That's it for this video. You need to do the exercise 26D worksheet questions now. If you have any questions, like always, you can stick them on Google Classroom in the comments below or shoot me an email. Thanks and see ya.